A lightning detector is a device that detects lightning produced by thunderstorms. The device was invented in 1894 by Alexander Stepanovich Popov. It also was the first radio receiver in the world. Lightning detectors and weather radar are used together to detect storms. Lightning detectors indicate electrical activity, while weather radar indicates precipitation. Both phenomena are associated with thunderstorms and can help indicate storm strength. Thank you for watching. For more educational videos, please subscribe to WizScience on YouTube or visit wizscience.com.
This is the summary of Appropriating the Weather, Wilhelm Jacobs and the Construction of a Modern Meteorology by Robert Mark Friedman. Robert Mark Friedman has written a lucid and engaging narrative of the career of Wilhelm Jacobs and his Bergen School of Meteorology, originators of the concept of the weather front.
A Birkeland current is a set of currents that flow along geomagnetic field lines connecting the Earth's magnetosphere to the Earth's high-latitude ionosphere. In the Earth's magnetosphere, the currents are driven by the solar wind and interplanetary magnetic field, and by bulk motions of plasma through the magnetosphere. The strength of the Birkeland currents changes with activity in the magnetosphere. Small-scale variations in the upward current sheets accelerate magnetospheric electrons which, when they reach the upper atmosphere, create the auroras borealis and australis. The currents were predicted in 1908 by Norwegian explorer and physicist Christian Birkeland, who undertook expeditions beyond the Arctic Circle to study the aurora. He rediscovered, using simple magnetic field measurement instruments, that when the aurora appeared the needles of magnetometers changed direction, confirming the findings of Anders Celsius and assistant Olaf Hjorter more than a century before. This could only imply that currents were flowing in the atmosphere above. He theorized that somehow the sun emitted a cathode ray, and corpuscles from what is now known as a solar wind entered the Earth's magnetic field and created currents, thereby creating the aurora. This view was scorned by other researchers, but in 1967 a satellite, launched into the auroral region, showed that the currents posited by Birkeland existed. In honor of him and his theory, these currents are named Birkeland currents. A good description of the discoveries by Birkeland is given in the book by Jago. Thank you for watching. For more educational videos, please subscribe to WizScience on YouTube or visit wizscience.com.
So we're outside the old Cavendish laboratory on Free School Lane in Cambridge, and this is where C.T.R. Wilson was working when he invented his cloud chamber in 1912. We're going to go and visit the new Cavendish laboratory and meet Professor Malcolm Langmuir, who's responsible for the Cavendish Museum archive where the old cloud chamber is kept. I'm a particle physicist and I work on a detector at CERN on the Large Hadron Collider called LHCb. The reason I'm so interested in C.T.R. Wilson's cloud chamber is because it was the first scientific device that allowed us to see particles. It really revolutionized our understanding of the subatomic world.
C.T.R. Wilson is one of my great heroes. It turns out that we had very parallel career paths. Perhaps most important of the lot, we were both very keen mountain walkers. And of course, it was during his mountain experiences on the top of Ben Nevis that he began his work on the cloud chamber. The original experiments were intended to work out the conditions under which droplets would fall. So this is the famous Wilson cloud chamber, the version produced between 1910 and 1912. Here's the apparatus. Inside the chamber, you have water vapor, which is just on the border of supersaturation. And here we've got a large vacuum vessel, which is used in order to make the expansion occur extremely rapidly so that it becomes supersaturated, and then whenever any single particle goes through, so it will leave a track of ionized particles, and each of these is a condensation center for the water droplets.
And then you get the tracks.
And then you get the tracks. Yeah. That's the way it works. Very, very clever.
Has this ever happened to you? You tune in radio when all at once, what makes all that static? Back in the early 1930s, there was a young scientist who liked to listen to static, Karl Jansky. He wanted to find where the static came from and get rid of it.
Over at the main campus, New Mexico Tech is also on the front lines of another battleground. Taming dangers in nature is one mission of New Mexico Tech's Langmuir Lab. Scientists work more than 10,000 feet up on Magdalena Ridge, a place that spawns powerful thunderstorms every summer. One focus, lightning.
We don't understand how it gets started, and so a lot of our measurements, and this is why this lab exists, is that we make measurements on the ground and in the thunderstorm itself.
New Mexico Tech researchers discovered that pointed lightning rods dating back to Ben Franklin did not protect structures as well as rods with rounded tips. Rounded are now code.
Around the world, at any given moment, 2,000 thunderstorms are churning through the sky, producing up to 100 flashes of lightning every second. Lightning might seem like something we've got all figured out, but in fact, the details of the physics behind those flashes is still a bit of a mystery. Los Alamos National Laboratory studies lightning because it produces signals similar to those from a nuclear explosion. That understanding is helping us develop better instruments for nuclear test ban treaty monitoring, and, in the process, allowing us to answer a lot of questions about lightning itself. For example, what initiates lightning? Some say it's caused by cosmic rays scattering enough electrons through the atmosphere to get a current going. But recent research conducted by Los Alamos scientists and their collaborators strongly suggests that lightning actually arises from areas of extremely high, localized electric fields, not from the long paths that a cosmic ray-induced event would require. We're also learning that lightning can be a useful tool. Research shows that enhanced lightning rates can indicate severe weather. Maybe someday our understanding of lightning will allow us to use space-based lightning detection to predict tornadoes and other severe weather events with enough lead time to prevent casualties. Until then, Los Alamos will keep studying and better understanding those mysterious, energetic streaks in the sky.
Lightning is more than nature's fireworks display. Research has shown that lightning is an excellent early warning indicator for approaching severe storms and the development of tornadoes. This data visualization shows actual lightning measurements captured by a remarkable array of ground-based lightning detectors, capable of tracing how lightning propagates through the atmosphere. From space, the intersection of lightning and its corresponding cloud fronts becomes clear. That's why, on the nation's new environmental satellite, called GOES-R, an advanced lightning mapper known as GLM will survey much of the Western Hemisphere for atmospheric flashes. According to GOES-R scientists, this technology could help provide critical minutes of valuable warning time in advance of approaching severe storms.
Where there's lightning, there's a strong chance for severe weather. The revolutionary Geostationary Lightning Mapper, or GLM instrument on the new GOES-R satellite, will give forecasters powerful new data for when to recommend that people in a storm's path take shelter.